Hello, everyone. Welcome to the third week, the first webinar. This is me, Ahmed Al-Garhi, and today I will be your moderator for this session. Let me introduce my friend, Dr. Ahmed Gom'a. Ahmed is currently a fracturing fluid engineer for unconventional reservoirs in BP, United States. Ahmed previously worked as petroleum engineer for Saudi Aramco for 1 year. Also, Ahmed worked as a research scientist for Baker Hughes for more than 5 years. Ahmed, his major is, including hydraulic fracturing fluid, acid stimulation, fluid diversion, and engineering treatment design in general. He holds a bachelor degree and master degree from Cairo University in Egypt, and also a PhD from Texas A&M University in the United States, all in petroleum engineering. Ahmed published 10 granted patents, US patents, and 15 patent applications, 13 journal publications, and 70 conference papers. Dr. Ahmed, we are happy to have you today. Please, we are waiting for your presentation. You can start.
Thank you, Dr. Ahmed, for the nice introduction, and thanks for the invite for this session, and also thanks for the audience for having for listening to this session in advance. Okay, my session will have a title Introduction to Acid Simulation. So I hopefully by the end of this session you will have a nice idea about acid stimulation, what you expect to do, and how you can do it. How can you design the job? So let me start with simple definition. What acid stimulation is? Just to highlight, it is like unsteady type of injection. So it's not steady state, it's actually unsteady state. It's non-isothermal. So actually temperature will change as you are injecting your fluid, as the fluid is reacting. And also is a 3D type of fluid. It's not linear flow, it's not radial flow. It actually is almost like if you have a perforation, we are talking about spherical flow. So we have a flow in the 3D pattern. And as the word acid mean, we have a chemical. So we are injecting a chemical that will react with the rock. This reaction will allow the rock to be dissolved. And as we are dissolving the rock, we have a continuous variation of both porosity and permeability. So as you are dissolving the rock, you have increase in the porosity, and hopefully also will have increase in the permeability. However, at any reaction, you will have a reaction product, which will also sometimes be precipitate. And as you have a precipitation, you will have a decline in the porosity and also a decline in permeability. So hopefully what we hope at the end of the job, the amount we dissolve, the porosity and the permeability we create will be in general much higher than the damage or the precipitation that we create, aiming at the end of the job to overall enhancing the well productivity. And as another aim, if there is any scale, we should remove it, especially scale existing in the existing natural fracture or the creating fracture, and also reduce the skin factor by removing or bypassing any near wellbore damage. So that's like a quick definition about the acid stimulation. However, the main question that you should ask yourself, like when the acid treatment is needed, like is my existing well need to have an acid treatment or not? A lot of people will ask themselves this one, and a lot of people need to know exactly when they apply the acid for their wells. Acid, we do not bump it just to increase the productivity. No, acid only bump it when you have damage. That's the only case that you bump the acid. And that is the objective of the acid. Acid either to bypass the damage or remove the damage. And hopefully by removing the damage, you are restoring your formation, or you are restoring your permeability to the original condition, and hence you are actually increasing your damage well permeability to a higher value. A second question you'll ask yourself, is my well has a damage or not? So damage by definition is unusual or unexpected reduction in the oil production. So each well from reservoir engineering point of view, it has its own decline curve. So you know this well supposed to produce a certain barrel at a certain pressure. If you are seeing you are reducing or how can I say it, or sometimes if it's injector well, you are injecting less than what your actually model say, what your reservoir simulation say, in this case, most likely you have the damage. And the damage can be really gradual, is not significant, is not really high. And that's happened in the cases like when you have a calcium carbonate scale. And this can be a very building slowly with time. And the decline that you'll have in the oil and gas production will be slowly with time. A second one can be really rapid, can happen suddenly. And that's happened when you are plugging your formation or plugging your perforation, or actually plugging your tubing. This can happen very quick and very extensively. A second one, when you start to notice there is an increase in the gas oil ratio unexpectedly, and increasing the gas oil ratio is one of the things that you like to see, because when you have increasing gas oil ratio, this means you have additional pressure drop that you are not expecting, and this additional pressure drop increasing the gas oil ratio part. And the final one, which is a more, how can I say, it's a more nightmare for us, is the water cut. When you have start to seeing a really high water cut. When you start producing water, when water become higher, as a production engineer or the completion engineer, you start to look really, how can I say it, worried about your well. Water is also coming with a lot of issues. Water can come in with a corrosion. Water can come with a sand production, can cause some emulsion to the well, and as well as bacteria. So water is like one of our nightmare, let me say this way. So when you see a lot of water coming, you need to be careful, and you need to be knowledge where this water coming from and what is the source of the damage that can water happening to us. So what type of acid simulation we are talking about? Mainly, we have two types of acid simulations that a lot of people, when they mention that simulation, they talk about either matrix acidizing or fracturing acidizing. And the main key factor is how you're actually bombing your job. In case of matrix acidizing, you are injecting at a rate and the pressure usually less than the fracture gradient. So you are not creating a fracture, you are bumping less than the fracture gradient. You are not breaking the formation, you are bumping the acid to react and flow in the porous medium and react in the surface of the pores. And we have main two types, what we call sandstone acidizing, and the other type is carbonate acidizing, which depend on the type of formation you have. If you have a sandstone, in this case, that's called sandstone acidizing, and it has a special acid system that can work for sandstone. If your formation is carbonate, in this case, you need to have a carbonate acidizing, and there is acid system that's actually specially for the carbonate part. The second type is the fracture acidizing, and you can, I think, it's easy you can guess. In this case, we are bumping with a rate and the pressure higher than the fracture pressure. And in this case, we're actually breaking down the formation and bumping the acid in a frac type of flow, not in a porous medium anymore. We are bumping the frac, and the acid will actually react with the surface of the frac, not inside the pores. There is definitely some leak off that the acid will react in the pores, but the main job here is the acid to react with the surface of the frac, trying to etching the surface of the frac and create what we call heterogeneous surface etching. That will help after the, how can I say, the closure. This heterogeneity will not make it completely sealed when the frac is closed after the treatment, and will create buses so that hydrocarbon can be removed easily out of the well. So that's like a big overview about the acid simulation and some definitions that can help us in the next part of the lecture. So what is the acid types that we are typically bumped for oil stimulation? Acidizing can be defined based on the chemical classification can be either inorganic acid, and we have a two main type, hydrochloric acid and hydrofluoric acid. And just to highlight, when we are talking about HCl, which is the hydrochloric acid, this is the acid being mainly designed for carbonate formation. HCl is one of the main acids that can dissolve carbonate formation. The other type, the inorganic acid, which is called HF or hydrofluoric acid, and this is the only acid that can dissolve sandstone, can dissolve silica. That's why when you hear sandstone acidizing, you should keep to your mind that we are talking about hydrofluoric acid, as it's the only acid that can actually dissolve the sandstone. None of the other acids that been in the industry can dissolve in the sandstone except the HF. Therefore, any sandstone treatment must have somehow a way that contain an HF. Then we have another acid based on the chemistry origin, which is organic acid. This came from organic component like acetic, formic, citric acid. And as an engineer, we are really good at blendings. We like a lot of blends. We like to blend different acids to get a better results and to get a more optimized system. So you can have a blend of HCl, HCF as a complete blend between organic acids. We also can have a blend between just the same family of organic, like acetic formic, or formic citric, or citric acetic. And then you can have a blend of both, some organic, some inorganic, like formic HCl, or formic HF, or citric HF. So you can do a lot of blends, and that is actually, as engineers, that's one of the best areas that we are doing. We also, in optimization, we try to get the best design for the best solution. Then the last category we have is what we call special acids, which acids we use it only for special situations. Like you have a really extremely high temperature reservoir, or you are really in a remote area that you cannot pump HCl or HCF. In this case, you are going for a special acid. Cost of this acid is extremely high, and usage, I will say it's a limited usage. However, in some cases, we need them. And example of this acid like aminocarboxylic acid, GLD, MSA, EDTA, there is a lot of family for this one. However, we just use them very narrow usage, but under a special condition only. So let's cover the main acids that we usually pump in oil field industry. The first one and the most popular one is the HCl. It has a lot of advantage, and we like this acid a lot. First, the concentration. You can have a wide range of concentration from 3% up to 28%. So you have a, like, how can I say it, a border type of design of concentrations that you can use. HCl being delivered to the field at concentration of 31%. So that is how the way that you start with it. You get it in the field with 31%, and then you can dilute it with water to the percentage that you'd like, based on the applications that you are recommending. A very good point about it is the dissolving power. HCl is a very good dissolver. It can dissolve really high. We are talking about, it can dissolve around, how can I say it here? 1.7 pound of calcium carbonate for each 1 gallon of 15 weight percent. Imagine, so if you are diluted to the half, you almost get really huge dissolving power. We are talking about 1.7 pounds for each 1 gallon of material. Let me write it a better way. So it's a very dissolving chemical, can dissolve a lot of material. And we like it too much because of the cost. We're talking about a really cheap acid, almost $0.7 a gallon for 15% HCl. So it's pretty cheap. And from cost point of view, it does not cost a lot to consider this treatment. And one of the things that also very good is the reaction product. When HCl react with a calcium carbonate or calcium or dolomite, which is calcium magnesium carbonate, all the reaction product is water soluble. As we can see here, the reaction product. So I have here the reaction rate between HCl and calcium carbonate, and the reaction product will be calcium chloride, which is salt, and that can be dissolved quickly, CO2, which is gas, and H2O, which is water. So we don't have anything that can cause any damaging or precipitation. Again, when it reacts with dolomite, which is calcium magnesium carbonate, you will have the calcium chloride, magnesium chloride, both salt, very high soluble. Again, CO2 and water. So we don't have any precipitate. We don't have anything that can cause any damage. So HCl can be a perfect choice. And again, like one of the things that you like to have is what's your start of pH. Usually when you start with this, the pH of the fluid at initial condition is 0. And a pH after trialing is a pH of 4. I wish to have you in class to ask you why do you think the final pH will be 4? Because of the CO2. CO2 will not bring the pH completely to 7. You still have CO2 that have been dissolved in the water that make the pH 4. So you can actually judge how your treatment is going. Be sure that all the acid being consumed by checking the pH of your flowback fluid. So you know, as you are injecting, you have a pH of 0. And as you're producing the fluid, you have a pH of 4 as evidence that all HCl that you are pumping is consumed. And as we are saying, there is no damage. There is nothing can be causing any precipitation or anything. However, it is a tricky to design with HCl because a lot of things. First, corrosion rate. HCl also can eat your pipes, especially at really high temperature. So you need to have additional additives with HCl to reduce any corrosion for the pipes that you are injecting with. Second, faster activity. HCl react in seconds, very high reactivity. So sometimes if you like to have some time to be able to inject your HCl deeper inside the formation, it's a tricky with HCl. So you need to design your job pretty well to be sure that to overcome the faster activity. Sometimes we add additional chemicals to reduce this reactivity rate, like polymers, like VS, like emulsion or foaming. A lot of things that we can reduce the faster activity of HCl. Another concern is the compatibility with the rock and the reservoir fluid. Mainly, let's start with the reservoir fluid. If you have asphaltene. If you have asphaltene is precipitate with when you have HCl. So you need some other additives to be sure the asphaltene will not precipitate. Second, if you have a clay in your formation, especially a light kaolinite, this is one of the clays that actually when it's HCl, it breaks into pieces and cause a lot of fine generation. So if you have a really high clay content, most likely HCl is not a good acid for you. And also if you have iron, especially either in the formation when inside your clay, like if you have iron hydroxide, that's one of the concerns that you'll have. Because iron and asphaltene will cause a sludge and cause some damage that HCl will not remove. They only need to remove it using solvent. So in this case, we need to have also additional additives like iron control agent to be able to overcome any concerns we have from the compatibility issue. And as you can see, like additives like HCl system, usually we bump it with a lot of additives. So the acid itself is cheap. However, the additives that you are adding is not cheap. So depending on the situation that you are in, like if you are really having a lot of clay, a lot of asphaltene, a lot of things, including all the additives, the price of the treatment will be going up just because of the HCl part. So this is for HCl. The second part is the hydrofluoric acid or HF. Again, this is the only acid system that can actually dissolve silica or silicate. In general, can dissolve clay, can dissolve silt, can dissolve feldspar, and definitely can dissolve sand. That's why when you should hear, like when you listen to HF, it should come to your mind, it is a sandstone treatment. We do not use HCF except only for sandstone. HCF can remove whatever HCl cannot remove. So whatever HCl particle or material that cannot dissolve by HCl, usually HCF will be able to dissolve this amount. And a lot of time, actually, we combine both HCF and HCl. The reason I will discuss it is my next slides, because HCF is a good asset to dissolve. However, HCF develop a lot of reaction product, insoluble reaction product, that's actually is not good and can significantly reduce your porosity and permeability, and can significantly, how can I say it, make the job that you are trying to improve your production, give you the opposite direction. Therefore, when you are talking about sandstone acidizing, you need to be really careful about how you're designing your job. What's the post-flush and pre-flush that you're bumping, and how you're bumping your job. And definitely, as I said, like, don't bump, especially HF, don't bump HF until you're extremely sure that you are bumping, you have a damage that need to be removed by HF. One of the other concern, as you can see from the diamond, about the how can I say, the SDS, or the characteristic of the HF, it has in the health part like 4. This is one of the nasty chemical that you will have in the location. So you don't like to breathe it or touch it or anything. So from health point of view, that's not a good chemical to be around with. We can use HF up to 350. We can inhibit it. We have no problem. We bump the job again before at really high temperature, which is a good benefit of having this one. And again, we are mainly use it to dissolve the silica or sandstone. We are talking about actually good solubility, 1 gallon of 12% HCl and 3% HF. And that's also how we are trying, the best way to write the concentration of the HCl HF system. And we usually call it mud acid, 12% HCl and 3% HF. It dissolves 0.17 pound of sand. Just remember, like, it's 15% HCl can dissolve 1.7 pound of calcium carbonate. But that's another type of formation, but just to highlight how this material is. And you are talking here about 3% of HCF to dissolve 0.217. So we're actually having good dissolving power for this type of material. This is some chemical reactions about HF and how we are bumping it. The first one I would like to highlight it, like when the HF react with a calcium carbonate formation. Immediately it produces what's called calcium bifluoride, and this material is actually insoluble. It will precipitate immediately. And that's like a point or a cut for us. Like, if you have a formation, even sandstone formation that has a high calcium carbonate content, usually, like, people say like above 20%, we never bump HF, because like you will have a calcium fluoride precipitation and significantly reduce the porosity and permeability. And instead of having enhancement, you're most likely increasing your damage. So you do not bump HF in a formation that has a high calcium carbonate content, or definitely a carbonate formation. However, if you are bumping with a formation that's pure silica or really high content of sand and clay, you can see the reaction is happening in 2 steps. The first, when the HCl reacts with the sand itself, it produces what's called flocelic acid. And the same is happening when it's react with clay, like for example, like bentonite. It produces the same acid, the flocelic acid in both. Then this acid will react with the sodium and potassium, either exist in the clay or actually exist in your formation water causing some sodium flowsilicate or potassium flowsilicate, and this is the material actually that will precipitate. So in HF, you have like what we called secondary reaction or secondary reaction precipitation, because the reaction happening in 2 steps, and sometimes it happens in 3 steps. And this all the material is actually a precipitation. And that's a pretty, how can I say it, a pretty way to overcome this precipitation by designing. First, we combine HCl with HF. One of the reasons we have also like combining HCl with HF because of this material. This material does not precipitate immediately at pH of 0. It starts to precipitate when the pH starts to be greater than 2. So the reason that we have all the time HCl with HF is to be sure, like HF is the acid that actually do the dissolving, is the one that actually do the work and remove the silica. However, the reason that we have HCl is to be sure we are keeping the pH all the time is 0. Until you push all this material deep inside the formation, really away from your wellbore area, then the pH, when the acid will be diluted with the formation water, it will be diluted and the pH will start to increase above 2. At that time, there will be a precipitation. But this precipitation will not happen near wellbore area. It will happen far away from your wellbore area. And in this case, the negative effect you will have from this precipitation will be very minimized. And overall, you will get a good success from the HF treatment. Also, what if your sandstone formation have a slight amount of carbonate? Not really high, but you're still having some amount of carbonate. In this case, you cannot start with HCl, HF. Just to highlight, when you have a blend of acids, the strongest acid is the one that will first react. So when we have a blend of HCl, HF, HF is actually a more stronger than HCl. So it will react first. So the HF will react first. So if you have carbonate, HF will directly react with a calcium carbonate and actually produce a calcium bifluoride, which will precipitate. That's why we do not start always with HCl, HF. We start with HCl first. And the idea here to remove any carbonate, dissolve the carbonate before the HF, then behind it with HCl, HF to dissolve the silica, and a post flush of usually HCl to keep the pH 0 and push all the reaction product that's coming from here deeper inside the formation, away from the near wellbore, and that's will at the end you'll have overall enhancement for your production. So I hope that can give a good idea about HF. Let's move to another type of acid, which is the organic acids. As we discussed earlier, we have the main 3 types of acids that we call organic acid: formic acid, acetic acid, and citric acid. And this is, we can call the organic version of HCl. It do what HCl can do. So this one also can dissolve carbonate only. It does not have any ability to dissolve silica. So it actually dissolve carbonate or any carbonate or dolomite, calcium, magnesium carbonate. It has a much better than the HCl. First, it has a low corrosion rate. So it does not hurt your tube as much as HCl. And that's why we like it at high temperature. Especially we can inhibit it at high temperature pretty easily. So we can bump it at high temperature with a less concern. We still can add corrosion inhibitor to it, but organic, because it's a little bit, how can I say it? It's actually much weaker acid than the HCl. That's why you can easily bump it in a tube or in cases when you have high temperature. Organic acid become pretty good if your temperature is greater than 250 Fahrenheit. That's start when you start thinking really good about organic acids. Another part, if you are really bumping, the contact time between your acid and pipe will be high. So for example, in some cases, you might expect a day or couple of days a contact time between the acid and the contact time. In this case, HCl can significantly hurt your casing or your piping. So in this case, you should know, let's in this case use an organic acid. And a lot of time you are mixing the HCl with the organic acid, because actually organic acid like to control the iron. Organic acid sometimes can chelate the iron. You don't have any damaging coming from the iron from your case. One of the things, like iron also can precipitate and can significantly cause your damage to the formation and impact the result of your treatment. So having an organic acid will reduce the precipitation happened from iron. One of the things that I would like to highlight, like we said, like HCl, we start from pH of 0, and at the end of the treatment, the pH will be 4. However, organic acid, like formic acid, for example, you start from pH of 2, because this acid is not as strong as HCl, so the pH is not as bad as HCl, like as low as HCl, as 0. However, at the end of the treatment, your pH is still around also 2. Like organic acid is, how can I say it, is not a completely solubilized, is not strong reaction and does not work in one direction. It actually works in both direction. So it takes a lot of time to completely neutralize or completely consume organic acid. So, and that's a little bit good in the iron part, because a lot of precipitation happened when the pH is greater than 2. So keeping the pH all the time 2 is helping to reduce the damaging coming from the iron part. The second part we'd like to discuss is the acid additives. What additives we actually add in our treatment, and this is the main topic. Like I will just quickly highlight it, but that's actually is the main reason you select different companies. So you have a different surface company, for example, like Schlumberger, Halliburton, Baker, Weatherford, whatever company you have. The main difference between these companies is actually what additives they can provide to you. HCl, HF, formic, acetic, citric acid, all these acids are standard acids. So there is no much difference between them. However, the main difference between the different surface company is what acid additives each company can provide and how effective each additive is good. So when you are doing the design, you are selecting between different companies based on actually the additives that each company can provide to you. And you will have a long list of additives that are provided by surface company, and your job as the engineer working with a production company is to be sure that you select the right additives with the right concentration, and these additives is actually needed in your case. For example, the first additives and the most popular one is the corrosion inhibitor. And let me say it this way, there is no acid treatment without corrosion inhibitor. This is one of the main component and main additives that you are bumping. And corrosion inhibitor is organic material that it's actually a blend of a lot of material together. And the objective of this corrosion inhibitor to be absorbed in the metal of the pipe and work as a barrier between your acid and the pipe. So the acid cannot react directly with the surface of the pipe, casing or whatever pipe called tubing that you are injecting with. And you'll find, based on the acid, there's different corrosion inhibitor. So you'll find there's a corrosion inhibitor work for HCl, there's corrosion inhibitor work for organic acid, and there's a certain corrosion inhibitor work for HF. So it's not one corrosion inhibitor work for everything. And the best way to select the corrosion inhibitor is doing a corrosion test. For example, you are expecting to pump a 6-hour job, and your static reservoir temperature is 250 Fahrenheit. So what you usually do, you need to provide the surface company with the tubes that you are pumping through it. If it's a cold tubing, so you need to provide them with a part of the cold tubing or the cold tubing specification. If you are pumping through casing or pipes, so you need to provide this information to the surface company and ask them to run a corrosion rate test for you. And the acceptable corrosion rate should be less than 0.05 pound per feet square. So after you inject, complete your acid for the maximum time that you are expecting to your job. So if you are expecting you are injecting almost for 6 hours or 8 hours or 12 hours, you will do the corrosion test for the maximum time that you are expecting you are injecting your acid with. And you will select the highest temperature. You need to be in the safe side. And you'll ask surface company to run different corrosion inhibitor at different concentration, and you will select the one that will always give you less than 0.05 pound per square feet. That's like a standard amount. And just to highlight it, this will dissolve around 0.031 millimeter of your tubing. So 0.05 pound per square feet is a thickness that the thickness of the tubing that will be dissolved is a very small thickness, 0.031 millimeter of the tubing, and that is the acceptable surface. More than this one is not acceptable by the designing engineer. And one of the things you would like to be sure there is no pitting. Pitting is like you have like a hole or a small area that the acid is focusing in the pipe and attacking it significantly. So also no pitting. So this is like the first additives and the most important one. The second one, what we call corrosion inhibitor intensifier. And just to highlight, when you have a temperature above 250 Fahrenheit, usually corrosion inhibitor by itself is not that good. So you have like some sort of, I will say like a assistant or catalyst, some additional chemical that you need to enhance your corrosion inhibitor performance. And that's called intensifier. And as intensifier, we have only two types, either formic acid or potassium iodide. That's the two main components that we are using them. And usually this intensifier is used at above 250 Fahrenheit. Sometimes you can use it at 200 Fahrenheit if you really have a special material or your contact time is too high. In this case, we can use it at lower temperature. But for example, if your formation temperature is 150 and you see corrosion inhibitor intensifier, you need to request from the surface company why we are adding this one, because usually intensifier needed at a higher temperature. Third additives, what we call iron chelating agent. As we said earlier, like iron is one of the mineral that if it exists in your formation, it can cause a lot of issue, mainly precipitation, especially at high pH when the pH go to above 2. So you need some chemical to cleave this iron, to remove it and keep solubilized as much as we possible. So we have like what we called, some people call it iron chelating agent, iron controlling agent, or iron reducing agent. So it's all have the same function, that you remove the iron or you make iron solubilized and not precipitate after the treatment. Then anti-sludge agent, that's you apply it when you have asphaltene in your well. So if you have asphaltene or expecting to have asphaltene precipitate, so you need to have something to eliminate this asphaltene to be precipitated out of the formation. The fifth additive is a solvent. And that's when you have a mix or you have a lot of organics precipitate in your formation and actually need something to remove it. One case, like I remember, like you can pump HCl in calcium carbonate, and we know like HCl and calcium carbonate react extremely fast. However, we notice that is like HCl does not be able to dissolve the calcium carbonate. And we will not be sure why until we see the actual sample. We see like the calcium carbonate was being covered by an organic material, maybe asphaltene, maybe paraffin, maybe any organic component that can actually that work as a barrier between HCl and the calcium carbonate, or the material that we'd like to solve. So that's why it came, we need to have a solvent. And a lot of time we bump solvent in front of HCl, especially in a black oil wells or the oil that has a lot of organic deposition, just to be sure that we are cleaning the surface of the rock, so allowing the HCl to be react and precipitate. So that's one of the main additives. You have it when you have an oil well reservoir. The final additives, what we called retardant agent, which is actually, it's something that can reduce the reaction rate of HCl. Usually we use a retardant agent with HCl. And this can be either polymer like gel acid, or actually a VS component, what we call viscoelastic surfactant. And both of them work as a viscifying the HCl and by having the higher viscosity, you will reduce the, how can I say, the diffusion rate of the HCl to the surface of the rock and make the reaction much lower. There is also additional type of retardant agent does not depend on the viscosity, by depending on either emulsion or foaming. You can emulsify it with the oil, or you actually can foam it with a natural gas, try to reduce the reaction rate component. I'm not sure if you have any question or anything, we can have it at the end of the session for the discussion. Moving to another part, which is the acid treatment. What type of treatment that we usually bump the acid for? So we have a different type of treatment that we typically use acids. The first one called pickling treatment, soaking or scale removal treatment, acid breakdown job, matrix acidizing, which is a both like one for sandstone, one for carbonate, and finally acid fracturing treatment. So I'll go for each one and why we need it and how we can do it. The first treatment is called pickling treatment, and here we are trying to clean the tubing. We are not trying to do anything in the formation. We are merely bumping the acid, or actually most likely circulating the acid. So you will have your well bore, and you'll have your perforation section. Let me have it like at the end. However, we come with a cold tube, with a cold tubing, and try to bump the acid and circulating away from the well bore. And the idea here is try to clean any iron, any rust in the tubing itself. So you can see I have here a picture of the metal before treatment, and hopefully that's what we would like to see after treatment. Any iron should be removed. We can do that for old wells and also for new wells. Any well that we are expecting to see any iron, or we are believing that the tube is not that completely clean, so we do what we call pickling. And the objective is to remove any irons out from the wells before we are bumping the fluid inside the formation. And usually we do this one before any acid treatment. So this is one of the recommended treatment that we do before bumping the acid inside the formation. Pickling, we are talking about a weak acid. So usually from 3 to 5% HCl. And as additives, usually you are having two only additives, corrosion inhibitor and iron control agent. That is the two additives that you have. There is no need for anti-sludge agent or solvent or any other additives, because you are not expecting to go inside the formation. You are only expecting to clean the well bore. So that's why you are only having two types of additives. And as I just said, like only do pickling before acid treatment or cleaning the tubing. A second one, what we called soaking or acid washing. And here we would like to merely clean the tubing from a scale. Like I have here a picture of a calcium carbonate scale. You can see like this is I have here the tube part, and all this thickness is actually a scale. And what you are actually would like to have to remove the scale. This scale build up with time. So you start initially seeing a small reduction in production until it's completely built, become big and completely plug the tubing. And it's completely plug the tubing, you will completely lose your well. So you are pumping acid just to remove this one and restore it to the original part. It can help also to remove any scale from perforation. And sometimes some of the scale will be in the formation phase. So we can bump the acid as formation phase. Again, when we are doing acid washing, our intention to not bump it inside the formation. We are just like as a maximum, or the maximum location is just the formation phase. Because we have a scale, we have a calcium carbonate, acid concentration will go higher. So typically we are using, for this case, around 15% HCl. That's our typical acid concentration that we typically use for this type of treatment. Again, we always have a corrosion inhibitor. And as we are talking about scale removal, and we are not expecting to have a lot of iron, so most likely we do not need the iron control agent, except if we are thinking there is iron inside the formation. In this case, you like to have iron control agent. Second, because we are reaching to the near formation phase, we need to have whatever chemical or whatever additives that need to make the HCl or whatever acid that we are pumping compatible with the formation. So if we are having oil well that we may have asphaltene, so we need to have an anti-sludge agent. So depending on the formation, we select the other additives. Third type of the job, what we call acid breakdown job. And in this case, we are pumping acid, which is also 15% HCl. And we are intentionally pumping through the perforation. Like perforation cleaning can be from scale or from debris after you have your perforation. So you are intentionally pumping the acid inside the formation. You will have a little bit of acid that can go inside the formation. And that's why you still, like, as always, corrosion inhibitor is one of your main additives. You're still having some formation compatibility and somewhat we call diverting agent. As you can see, like, you will have, in this case, I have a horizontal well with a multi-stage acidizing. So you have, like, after you injecting in a certain way, in a certain perforation, you need to plug this perforation and allow the acid to go to another one. And we'll talk about acid placement in a later point. For matrix, we have what we call sandstone acidizing. In this case, we are intentionally pumping the acid inside the matrix with a larger volume of the acid and most likely with a higher rate. And in sandstone, we are not, how can I say it? We are intentionally trying to remove any damage that can be happening from the workover or from the completion fluid that we are pumping. One of the things that we have about sandstone, we do not create what's called wormhole, which that's only happened in carbonate. So when we are talking about wormhole, it's only for carbonate. Sandstone acidizing, we are not having a wormhole. Sandstone acidizing, usually the sandstone acid or the HF react with the grain surface and just enhance dissolving this part that I'm highlighting in red, improving the porosity and the permeability. And if there is any fines or any particles that causing the damage, HF will be dissolving this amount, restoring your permeability to the original value. Again, the best way that you are inject in sandstone, you start again with HCl to remove any carbonate. Then you pump your main acid, which is the mixture between HCl, HF, and then finally overflush with HCl to keep the pH low and pumping your eliminate any precipitate happening near wellbore area, make it happen deeper inside the formation. There's different concentrations that you can select depending on your situation. If your damage is not severe, is pretty small, in this case, we recommend to have what we call diluted mud acid, which is HCl will be less than 7% and hydrofluoric acid will be less than 1.5%. Very small amount of HF. If your if your damage is normal, in this case, we'll go with what we call the regular mad acid, which typically between 7.5 to 12. And I believe like usually we go with a 12% and 3%. Let me see this way for regular mad acid. If you are really having a severe damage, in this case, we go with a higher amount, like almost up to 16% HCl and up to 6% HF. However, we do not go to this level of high HCF except if really needed, if the damage is extremely high. Otherwise, the main concern of having a high HF will be too high because of the precipitation part. It's a little bit difficult to deal with the higher concentration of HF. Another type of acidizing called carbonate acidizing, which in this case we mainly are talking about either HCl, acetic, formic, or a blend of these acids. And the objective when we are talking about acidizing and carbonate acidizing, we are not removing damage, we are not solubilizing damage. We are actually bypassing this damage. And the way that why we are bypassing it, because HCl is a pretty aggressive reactor and actually can significantly react with the carbonate, creating actually holes. This holds what we called a wormhole. And depending on the injection rate, the shape of the wormhole can be happening. So if you are actually injecting at a lower rate, usually we get what we call conical wormhole, which is a pretty thick tube. Like imagining like you are actually having a holes inside your formation. And at like what we call at the optimum, we got what we call dominant wormhole. And if really high rate, we got what we call branched wormhole. Let me have this is like a shape of the wormhole. Like imagine this is like, we did it in a 3D rock. So this is your well bore area. At the imagination, that's your like well bore. And side from it, you will have this wormhole. All this high permeability channel that will bypass any damaging you can have. One of the main characteristics of the wormhole is the injection rate. What's the best injection rate that you can pump best to get the best wormhole? So I am having here going from left to right is the injection rate part. So if you are injecting at low rate, what will be happening, what we call phase distribution. At a lower injection rate, acid reacts very fast, usually. So if you are not injecting at a really high rate, so the HCl will merely dissolve the surface of the core, will not be able to penetrate deeper. So if you do a little bit higher rate, you have what we call conical, which is still acid react merely with the surface of the core, but because of the rate is a little bit high, some of the acid will go inside and create some of the wormhole. But at the optimum rate, you will start seeing a good and nice wormhole pattern, as you can see from these two pictures. And that's what we call the optimum rate. That's why when we are designing for carbonate, we would like to bump as much as we can or as high as we can to be able to create this nice wormhole. This type of, at a lower rate, you will have the phase distribution and you will have also a well integrity issue. So you don't want to have this type of scenarios. If your rate become really extremely high, you will say what we call the branching. You'll get a main wormhole, but away from it, we'll have a lot of branching happening it. But this is not happening so often. So a lot of time we will like recommend or design based on this amount of the optimum wormhole. Also, if you go away from the optimum, you bump a lot of acid, but only, how can I say it? You create a certain length that you need for the wormhole to be dissolving. So you do not get any additional benefit. All the acid that dissolve more, you remove the oil, you remove the rock, but you actually do not get additional benefit in the permeability part. The final type of the acid fracturing is, the final type of the acid treatment is acid fracturing. And here we are injecting the acid to actually, to create a frac and and bombing at a higher pressure. Sometimes you are actually either create a new frac or you open a pre-existing frac. And the idea here is not to create a wormhole or to remove the damage. The idea here is trying to etching the fracture surface. So when it's closed after treatment, you will still having an open area that will be conductive and productive. So I have here a 3 scenario that you are actually bombing the acid frac. One of the scenarios, the first one, you are injecting a small amount of the acid that creates a heterogeneity surface, but the amount is not enough. You can see still like with a little bit closure of the opening area that you have here in the yellow color is pretty small. However, when you have a really good design of the job, you will be able to see you have a really open area after the acid frag that can actually become a good for the hydrocarbon reduced. If you are overflush or you are injecting too much acid, you will be weakening all the surface area. So when you're closing the frac, become like everything will be closed again and you'll have a really small area that will open for the flow. So in acid, the amount of the acid that you inject and the way that you're injecting is pretty important to have the good etching part and to have a good channeling. You do not want to have the acid react with the whole surface area. You would like to be selective in a small area to get the maximum benefit of the acid. The way that we bomb the acid, we do it in 3 ways. The first way is a pad, which is a non-reactive fluid, usually cross-linked fluid. And the idea here, we would like just to break the formation and create the frac. So the pad section is to just break down the formation and create the frac that we would like to have. The second, we bomb the acid, which will etch the formation. And usually we are talking about between 15 to 28% HCl. If the ready temperature is too high, we are talking about 300 Fahrenheit or higher. In this case, we would like to use either acetic or formic acid if the temperature is pretty high. Then finally, we always end with over displacement or some fluid that can allow us to inject the acid a little bit deeper inside the formation. So this is the third way or the 3 steps that you do when you are bombing the acid fracturing. The final topic of my slide today is the acid placement and what would be the best way to place the acid. Let me first start with the issue. When we have a vertical well, usually we have a heterogeneity in permeability. So imagine if you have a case that you have like the bottom part will be the high permeability, then the top part, the permeability will go low, and the lowest one will have it like the lowest permeability. And usually you are injecting from the surface and you don't have a control. Acid, like a liquid fluid like water, will go in the least resistance path. What's happening? The acid will inject and will go only to the high permeability formation and will keep injecting acid in this one. You will not see acid will go in the low permeability section here or here. Mainly the acid will go to this one. So after treatment, you will see yourself only treating one zone. So acid only become here, and this zone is not treated, and this zone is not treated, and that's what you don't need. You always, when you are typically doing acidizing, would like to have a good coverage of the acid through the whole zone, and that will be a good treatment. By treating a zone and leaving the other formation or the other zones untreated, that's not a good treatment design. So to have a good placement, we have a 2 types of placement technique. One what we called mechanical, which actually you use some sort of a mechanical equipment to better distribute the acid. The other called chemical, which we're using chemicals for diversion. Mechanical like cold tubing, Parker, bridge plug, and pole sealers. Chemicals, we have foam acid, emulsified acid, gelled, or in situ gelled acid. And just like cold tubing, that's a picture of cold tubing. In this case, you are actually go with the cold tubing to whatever depths that you are actually interested to treat and bomb the acid there. Then move cold tubing to another area and bomb the acid there. And move the cold tubing to the third area and bomb the acid there. So use a cold tubing to spot the acid in each location through the whole well. A second one like Parker. In this case, you set the Parker in the zone that you are like to treat and treat it. then release the Barker and go to another section and treat it, and keep going on section by section for the treatment. Bridge plug is the same concept, like usually put the plug, treat the zone, and then remove it, put another plug, treat the zone, and remove it, step by step. Ball sealers is like a ball, and that's actually seat in the perforation. So you are injecting first the acid that will go to the hypermobility zone. Then you pump the ball sealers that will actually plug the perforation. And as these balls plug the perforation, you'll not be able to inject the acid in this perforation anymore. So when you keep injecting the acid will go to the other perforation that does not have the ball sealers. In general, mechanical is a good way, and having the mechanical method, you are sure that this formation being plugged, and you are pretty sure that you have a good distribution of the acid. However, it has a lot of disadvantage. First, it only controls the fluid inside the wellbore. So if the fluid go inside the formation, you don't have any control where the fluid will go after it passed the perforation. Second, most of the time you need to have a casing and perforation type of treatment. So if you have an open hole type of treatment, usually mechanical method is a pretty tricky to be used. And the third and the most important part, the expensive. It's a pretty expensive to use. So the cost when we are trying to use a cold tubing or bridge plugs and release and Barker release it on and off become a pretty expensive technique. So you don't want to depend mainly on this one. That's why we will like the other part. There is a ball sealers, which is again applied for the perforation part, but additional to the mechanical, it needs a higher rate. Ball sealers need a higher rate for to be pumped. So you cannot pump ball sealers at a low rate. It will not sit in the perforation. So in the other side, you can have a chemical methods, which is actually pretty good. It can apply for all type of completion. It works by viscosity diversion, because all of this chemical will have a higher viscosity and has what we call non-Newtonian shear-thinning behavior. So non-Newtonian shear-thinning behavior is like a relation between the viscosity and shear rate, which is your injection rate. So this is the behavior. So what's happening when you are bumping, the shear rate will be high. So the viscosity will be low. So it's easier to bump. However, when it's go inside the formation, because you are moving in the radial part, your injection rate or your velocity inside the formation will go down. So the viscosity will become higher and higher as you go away from the wellbore area. As the viscosity go higher, it will plug the zone that you are bumping in, and actually will allow the next acid stage to go to a certain one. I will show you a diagram how it works. Definitely, it controls the fluid inside the wellbore and also inside the formation. And actually, we noticed that when we are bumping this type of chemical, we got a much efficient wormholing pattern. We have mainly two types, what we call polymer-based and surfactant-based as a gelling agent or the chemical part. For polymer, it called also, there's some people call it as a self-diverting acid, and some people also as a viscosity controlled acid system. Let me go not this one, this one. So how the chemicals work, initially you'll have a hypermobility formation. All the acid will go to the hypermobility formation. Then when you're bumping this chemical, as this chemical will go inside the hypermobility, it will build the viscosity. And by building the viscosity, you see it will plug this one, because the viscosity here will be much higher than the viscosity in the upper part. And by having a higher viscosity, there is no flow will be able to go here. So the acid, the next stage, will try to go to the lower permeability. And again, you inject your chemical that will plug the formation here, forcing the acid to go to the top part. So at the end of the treatment, you will find all this viscosity will be higher for a certain time. It will break, and when you have the flow back, you're treating the whole zone. Actually, this was my last slide. If you have any question, I would like happily to answer it.
Thank you very much for the great presentation, as usual. I have many questions, but let me select like 5 questions. So someone asking, does acidizing change permeability and porosity, or just play with the conductivity, like in hydraulic fracturing?
Acidizing does not change the permeability of the whole reservoir. It only changes the permeability near wellbore area. So the effect there will not be that huge on the reservoir scale. That's why we said, like, when we have the damage part, because permeability near wellbore area will be higher, and if you have the damage, the skin factor will be higher. So let me go like, if you have your wellbore area, and if you are blocking to the reservoir, so when you are flowing, your pressure will be look like this. If you have a damage, you will have a much higher pressure drop, and that's the pressure drop that you're having from the damage. And that's how you define a skin factor. What is an acidizing? We try to actually moving from the lower curve to the upper curve and restoring to the original permeability. However, we are bumping the acid in almost 3 to 5 feet. If we're talking about acidizing in a matrix acidizing, that's a maximum that you can reach. So you will not be able to enhance the permeability of the whole reservoir. So you are mainly around your wellbore area. And this will enhance the productivity around the wellbore area only, but to the original value of the reservoir, not exceeding this amount. Acid fracturing is a different technique, because acid fracturing is changing the way from the well producing from, like, if you have your wellbore here, you have a radial flow. But if you have an acid frac, you change it to a linear flow type of behavior. And linear flow definitely will have a much higher impact in the production than just a matrix acidizing. So if you are really would like to change your well production type of treatment to get a much higher amount, so you are talking about acid frac, not a matrix acidizing. Matrix acidizing does not enhance the permeability of the whole reservoir.
Okay, so the next question, you mentioned something about a rapid decline of production as an identification of formation damage. And someone asking, is it the same for all formation types? I mean, the decline behavior, is it the same for all formation types?
Rapid decline is happening when you are plugging either perforation or plugging the tubing, and that can happen for all type of formation type, yes.
Okay, so another question about mud acid. Someone asking why we use mud acid in sandstone and why we do mixing.
Mud acid is a definition, meaning you have an HF, and HF is the only acidizing that dissolves sandstone. So without HF, you will not be able to dissolve any sandstone. So if you keep bumping HCl in a sandstone formation, it will not do anything, because simply HCl does not dissolve silica or sand. So you need an HF acid there to be able to dissolve the sandstone part. Why we need the mixing? Because as we have the reaction rate, HF will do a lot of precipitation. The reaction product from HF will precipitate. So you need to have the HCl with the HF to keep the pH low, like around 0, to make this precipitate does not happen immediately, to lower it a little bit so you can push it away from the wellbore area. So you near wellbore area, you have a clean zone. And this is, you can see the skin reduction type of performance.
Okay, so someone asking, a normal hydraulic fracturing job, do we use acids?
We use acid in normal only for breakdown, for cleaning the perforation. However, in normal hydraulic fracturing, we depending on the proban to create the conductivity, not the acidizing.
Okay, so the last question is someone did not get what you mean by ion control. He did not understand what is ion control.
Iron control is a chemical that can use to keep the iron solubilized and does not precipitate. So iron control can be either chelating or reducing part, like chelating it, make it a complex with iron and keep it solubilization, or reducing it from ferric to ferrous, and in this case will not be damaging.
Okay, so there's one more question. Someone asking in the chat section, why everybody in Egypt named Ahmed? Do you have an answer for that?
Sorry?
Why everyone in Egypt named Ahmed? It seems like he noticed there's a lot of Ahmed.
I don't have an answer for that.
I told them we have Muhammad also. So we have Ahmed and Muhammad. There's many people named Ahmed and Muhammad. So, okay, so thank you, Dr. Ahmed Goma, for the great presentation, and hope to see you in Marietta giving a lecture here. And thank you for everybody. Thank you.
Thank you.